psi f has a complicated state. We measure only, heavy ion collisions produce thousands of particles. We measure many of them, but not all of them. We don't measure all the possible channels, so we don't know psi f. U, the evolution operator, is an awfully complicated thing, and basically we don't know much about it. And psi I, this is what we want to learn about. We want to learn about the initial state. So, the situation looks somewhat hopeless from this perspective. However, things are not that bad. I mean, we know how to handle such situation. We don't know what psi f is, but we can select degrees of freedom. We are going to select, we are going to make measurements, so-called inclusive measurements, in which we select degrees of freedom. So we give up degrees of freedom, not quite yet. We give up the possibility to describe entirely the evolution of the system. We are going to focus on some specific degrees of freedom. And those degrees of freedom will depend on the condition under which we do the experiment. And this is where relativity will come in. Relativity will come in several ways. Let me remind you that in the collision of two heavy nuclei at high energy, the two nuclei are coming toward each other at a speed which is close to the speed of light. And there is a factor which, the gamma factor, which tells you by how much the lengths are contracted in the direction of the motion, viewed, say, in the center of mass frame. And that gamma factor is typically of the order of square root of s divided by the mass of the proton, say. Well, square root of s, where s is the square of the center of mass, the total center of mass energy. So if square root of s is of order 1 GeV, you see that gamma is 1. There is no much effect of relativity. The degrees of freedom which you are dealing with are those basic degrees of freedom of a nucleus made of proton or neutron, and you are going to do what used to be called low energy nuclear physics. We're going to describe the collision in terms of individual nucleon-nucleon collision. There could be mean field effects, exchange of mesons, etc., etc. This is a complicated game, but which has been played for many years, and basically the situation is more or less understood. Now, when you go to ultra-relativistic collision, let's say 10 GeV, that was done with the SPS or in the 80s, gamma is about 10, so you see the nuclei starts to be contracted. And let me move right away to Rick. Rick energy is the gamma, square root of s is of order 100, gamma is of order 100. So a nucleus like lead or gold nucleus, which is about 10 Fermi big, I mean the diameter of the nucleus is about 10 Fermis, will look like a contracted pancake of thickness of about 1 Fermi. If you go to the LHC, and let me be optimistic, that we take 10 TeV collision, we're not yet there. The gamma factor is 10,000, and at that point, you see the nucleus looks like a fraction, the thousandth of a Fermi thick. Okay? Then in that condition, the fact that there are nucleons inside the nuclei doesn't play too much a role. And at that energy, the main degrees of freedom, this I will call an abbreviation F, main degrees of freedom are gluons. Now, one should be careful because, as I said before, main degrees of freedom depends very much on what you want to do with them. I say these are gluons, but it's not always the case. And to explain that a little bit better, I need to do a little bit more. Let's assume that just assume that there are constituents for the moment inside the protons or inside the nucleons, and look at a typical collision. What will happen in the collision is that two of these constituents will collide and produce particles. This is collision. This is the outgoing particles. These particles will be characterized by some transverse momentum, called P transverse, and by longitudinal momentum, which I will denote by x times, let me call this momentum K first, and this momentum P, and P is essentially PZ. So the momentum, which I will denote by x times PZ, where x is a fraction of the incoming nucleon longitudinal momentum. Now, if the collision is 2 to 2, and if I sit near the central rapidity, you can easily establish that the x is given by K transverse divided by square root of s. I guess that's what it is. And if you want to move away from central rapidity, you have to neutralize this by plus or minus y, where y is the rapidity along the beam axis. Let's ignore it. Let's set y to 0. So you see, the particles, most particles which are produced have a kT which is of the order of 1 GeV or below. 90% or something like this of the particle. So if you are interested in the mechanism which produces most of the particles, then you are going to look at particle and a constituent which carry fraction x, which is of the order of 1 over square root of s expressed in GeV. Now you see that if you are at Rick, that means x is of order 10 to the minus 2. At the LHC, it can be 10 to the minus 3, 10 to the minus 4. And if you go into a region of high rapidity, forward rapidity, say, you can reduce this factor by an exponential amount. I mean, 10 to the minus 6, minus 7 can be reached at the LHC in the forward rapidity region. So that means that for all what concerns the dominant particle production, small x constituents are the relevant degree of freedom. And basically, this is what the lecture will be about. The physics of this small x degree of freedom. Before I say more about that, let me emphasize the fact that if you're interested among the things that you want to see in the final state, you want to see so-called hard probe, let's say a jet, for instance. A jet will involve a much larger value of kT. A jet will be produced with an energy of in the range of 100 GeV, typically at the LHC. So 100 GeV divided by 10 to the 4, 10 to the 3, it's not a small x physics. So you're going to, depending on what you want to look at, you're going to select in the nuclei constituent which carry different values of x. But I will not say much more about, I won't say anything about jets, except a few remarks in passing, but focus in the rest of this lecture on the small x physics. So why is that interesting? Well, it is interesting because we know for measurement, which we have done at ERA, at days we know that these are essentially deep inelastic scattering of electrons or muon on protons, and some experiments on nuclei as well. We know that the number of gluons in a proton, and I will make this notion more precise in a little while, increases with decreasing So, I mean, this is well established. Of course, we don't know, I mean, there are many things we don't know, but the fact that the density of gluons grows with energy is something which is well established. And therefore, the physics of small x physics in this high energy domain is a physics of high density systems of gluons. And there are a lot of interesting phenomena which are expected to occur in this context. So the lecture will be precisely about this phenomena. Let me just write here a keyword. The keyword is that this growth of the gluon density is bound to stop for some reasons that I will explain later. And it stops at a characteristic momentum scale. Just momentum scale, which is called the saturation momentum, and which is denoted QS. And the physics of saturation is what I want to explain to you in these three lectures. Okay, so see, I should watch out the time. Oh. We started at 8:30?
Yes.
8? It's
Yeah, something like
okay. Okay, so let me now enter more quantitative stuff and remind you how we know about all this, and say a few more words about deep inelastic scattering, because this is how Barton picture emerges. So, deep inelastic scattering. We consider a typical experiments in which you have a photon coming in. So this is a proton. I have a virtual photon, typically coming from an electron, which is interacting with the target. And in the regime I consider, the virtual photon will hit a quark. And there are a number of variables I need to introduce. I call Q the form momentum of the photon, K the momentum of the struck quark, and this momentum is T plus Q. And the idea of the main part of the naive Barton model is to assume that this struck quark is on shell, which means that K squared is equal to 0, and it's also equal to K plus Q squared. So from there, you easily deduce that you take the scalar product here, 2k dot q plus q squared is equal to 0. We are everything wrong here, no? And let me introduce now some notation. I call k x times p, where p is the form momentum of the proton, this one. So this is the usual Feynman variable, x times the momentum. And this momentum is essentially longitudinal. And then I denote q squared is minus little q squared, because the photon is a virtual photon, is space-like, and the q squared is negative. The little q squared is negative, and so the change of sign here. And then there is, so under this condition, you can establish the following equality. If I denote by x locant quantity q squared over p over k dot q, it's a simple exercise to show that this is equal to x. And what this says is that indeed under the condition I have indicated, that the photon scatter is essentially absorbed by the struck quark. This is essentially elastic scattering on the individual constituent of the proton. So now, just hesitating whether I should skip something and leave it as exercise or continue a little bit. I will say more right now. So let me denote by S hat the center of mass energy of the proton-photon system. So S hat is the sum P plus Q squared. And this is equal to P squared, which is the mass of the proton, plus Q squared, that's a photon, plus 2P dot Q. M squared I'm going to ignore, because I have a high energy and I'm assuming Q squared is big. So you see that under this condition, the P dot Q can be expressed in terms of S. And the result is that X, remember P, yeah, remember K, sorry. What have we done? P dot Q. Well, let me skip the details. What I want you to find out is that X will be equal to Q squared over S hat plus Q squared. Now, I want to work in a regime where Q squared is big compared to the lambda QCD squared. And the reason for that is I want to have the transfer momentum induced by the transverse photon, which is large compared to the scale which governs the internal dynamics of the proton. What it says here is that the scale of the internal dynamic is lambda QCD with factors of 2. But what is said here is that I want to have, in terms of time scale, I want to look at the proton on time scales which are very short compared to the time scale which are characteristic of the internal dynamics. So on this very short time scale, the quarks which are inside the protons can be considered as free particle. And that's the basic idea of the proton model. It's not that the proton is made of three free quarks, of course, that's nonsense. But on very short time scale, you can ignore the fact that the protons, that the quarks in the protons are strongly interacting. That's one of the essence of the proton model. And this discussion about time scale will come up later. And now, because I want also to work at high energy, where S is much bigger than Q squared, this is a high energy limit. Then X is much more than 1 because of this formula. So you see there are two things here which are involved. One is the fact that I will look at the object on a very short time scale, so you can think in your head as I'm doing with this type of experiment, but it won't be different in heavy ions. I'm doing a snapshot of the state of the system with a very fast time resolution. And on that very fast time resolution, I don't see that the quarks are interacting. And now if I also go to very high energy, the proton and the photon have a very large momentum, the frame in which I'm looking at, then the constituent that will be involved will carry a small fraction of the momentum. Now, of course, in the case of deep inelastic, these have to be quarks. So these are not valence quarks, these are quarks which are produced by the gluons. Gluons can decay into QQ-bar, and these are the quarks which you're going to see inside the proton at very high energy. These are called C quarks. Okay? Now I need to say more about the structure of the proton, and to do that, I will say a few words about light cone perturbations here.
Just short question. From this inelastic scattering experiments, we know the so-called Hartmann distribution function. And do we know where actually the gluons start dominating over C quarks and so?
Yes. Now I mean, of course, this is a disadvantage of doing things on the board, but I cannot show you a picture, but I can draw it roughly, the picture, if you, the distribution of quarks, I mean, looks like this. This is 10 to the minus, this is x, and this is, maybe I have a plot somewhere, because it will not be too stupid. Let me just, I should give you a reference for this as well. Oops. The gluon starts to dominate already at 10 to the minus 2. Well, you probably have seen these plots. I mean, I'm referring to this side of plot from here collaboration, I mean, from the various collaborations, both H1. So this is typically a valence quark. Let me not. And this peaks slightly above 10 to the minus 1. And this is 1. And 10 to the minus 2 is somewhere here, 10 to the minus 3. And the gluons starts to build up, this is multiplied. So this, the gluons look like this. This is 5 times 10 to the minus 2 times x sub j. And this is a notation for the gluon distribution. So you see already, I mean, this is multiplied, I mean, this is divided by almost a factor 100. So already at 10 to the minus 1, 10 to the minus 2, the gluons are a significant fraction of the content. So let me now give you a hint of how we go and calculate what's the gluon content of the proton. And I will do that by doing perturbation theory. And I will use perturbation theory in various fashions. But at the moment, I'm just doing straightforward perturbation theory. And let's consider one valence quark in the proton. So this is a quark. This is a bare quark. Namely, the object which you have in the QCD Lagrangian. When you write the psi organ and you psi, the psi is what we call a bare quark. And now the quark field is interacting with gluons. And therefore, in the same way as an electron is a more complicated object than a bare electron, the bare quark gets dressed by radiative correction. The bare quark can emit a gluon. This is a gluon. And therefore, if you look at the quark, assume you have a probability to find the quark in a state which is bare. So the state which I will call Q, let me put double brackets here, will be some coefficient A times Q, let me note 0, which means the 0 here means bare, plus B times a quark and a gluon, plus etc. And have arbitrary numbers of gluons. And I will discuss what happens when you have many gluons very, very shortly. Now, this coefficient A and B, once you know QCD Lagrangian or Hamiltonian, you can calculate easily. And I will not do that explicitly. I will just give you some intuitive indication about the characteristic of such fluctuation. And perhaps it's best to think in terms not of this diagram for the amplitude, but in terms of self-energy diagrams. Basically the same, but and you're asking, I mean, the quark fluctuates into a quark and a gluon, and you're asking, the question I want to ask is, how long does this fluctuation live? Okay? So, the lifetime of the fluctuation is going to be proportional to 1 over delta E. Well, delta E is given by the energy denominator, or if you wish, by the amount of energy, of the violation of energy conservation during this process here. Now, what is delta E? Delta E can be easily calculated. I will put some label here. P, K, and P. This is K or P minus K. So delta E is simply equal to the energy of the particle K plus the energy of the particle P minus K minus the energy of the particle momentum P. So these are all massless particles. So I'm going to rewrite this as follows. The energy of particle with momentum K is kz squared, longitudinal momentum, plus k perp squared, transverse momentum squared, plus P minus K. Well, P is big, P is a quark, so I'm going to work in a regime where P, the momentum P is large, much larger than the momentum which go into this loop here. So I just write this as, and I'm assuming that most of the momentum is carried by this line here. So K is small compared to P, in other words. Under these conditions, this is just Pz minus Kz, and the energy of this guy here is just Pz. Massless particles, the energy is equal to the momentum, and the momentum is essentially the longitudinal momentum. Okay, so you see the Pz cancel, and if you expand the square root, assuming that Kz is big compared to K perp, what you find is that this is approximately equal to K perp squared divided by 2 times x times Pz. So this is delta E, which means that delta T, and this is the formula I want, is approximately equal to, well, just the inverse of this, 2x times Pz divided by K perp squared. So this is a simple but important formula. Gives you the lifetime of the fluctuation. So you see, if x is small, the fluctuation is short-lived. And this is what happened in the proton at rest. If you look at this small x fluctuation of the gluons, these are very short-lived fluctuation. Times in unit of Fermi of the C can be 10 to the minus 4, 10 to the minus 5. You don't see the fluctuation in the proton at rest. They are there, they contribute to renormalize the mass or other observable properties of the proton, but you don't see them. However, if you fix x and increase Pz, there is, hidden in this formula, there is a Lorentz time dilation factor, the gamma factor that I was talking about earlier. And this gamma factor dilates the time. So fluctuations which are very short-lived in the rest frame of the proton, if you look at them in a frame where the proton has a large momentum Pz, then this fluctuation becomes long-lived. And so long-lived that they are going to play a dominant role in the collision. These are the small x protons. This is a small x fluctuation have a lifetime which is short in the proton, in an ordinary proton, in the left frame, in the rest frame of the proton, which are amplified by the Lorentz dilation factor. And that's the main message here, which you should keep in mind. This formula, I want to use it a little bit later. Now, we can go ahead and calculate this addition process. The calculation is not different from what you do in electrodynamics, from the Bremsstrahlung radiation. And let me give you the result in terms of the probability to emit one gluon. So this probability I will denote by dp. It's a strong coupling constant, ultra strong. There is a color factor which I denote by CR. I will explain in a minute what CR is. Or pi squared. Then there is d2k curve over k curve squared, dx over x. And alpha strong, this is an H coupling divided by 4 pi. Now CR is just a color factor. It's a Casimir of the color representation. It's just NC. If you emit, if this object here is not a quark, it is a gluon. If this is a quark, this is NC squared minus 1 over 2 NC. Just a factor which is then the number of colors. But aside from this factor, the result is the same as you would get in PVD. So it's just the Remschrand formula. And what I've assumed here is that the photon or the gluon which is emitted is soft, it has a small energy, and a limited transverse momentum. And you see, the phase space for this emission is controlled by these two logarithmic factors here. dx over x is what you may call d omega over omega, where omega is the energy of the gluon, or dkz over kz, where kz is the longitudinal momentum of the gluons. That's the same thing. So this is telling you that small x gluons are amplified logarithmically, and that amplification is called the soft amplification. It refers to the fact that the gluon which is emitted carries a small energy, and because of this phase space available, there are a lot, in fact an infinity of soft gluons which can be emitted. And there is another factor which can amplify the emission, it's this ratio here. And that amplification is called collinear, because you see it favors the emission at small angle, limited Kepler. And it means that the gluons are preferably emitted along the direction of the emitters. Okay, so this is an important formula which, on which most of the following discussion will be based. Okay, so is it okay so far? You still with me? Okay. Okay, so now I'm going to tell you more about the distribution of these gluons and how this distribution changes with energy. Now I want to answer the question, how many gluons do you have in your proton? So that will bring me to an important concept, which is that of the evolution equation. And let me write directly one equation, which is the following. Well, this is what I want to get. Let me first define what I mean by a gluon distribution function. And there will be two such beasts, integrated gluon distribution and non-integrated gluon distribution. The word integrated refers to what you do on the transverse momentum variable, or the integrated vertical. So the integrated gluon distribution is denoted, this is traditional, it's denoted x times g of x and q squared. If you wish, x times g is the number of gluons which have a momentum fraction between x and x plus 3x in the proton. And that is equal to alpha strong. So this is for a quark. Alpha strong CF is for the quark, fundamental representation, log of q squared over lambda q squared. Now this result is obvious. I mean, it doesn't take too much effort to calculate it, because you are asking how many gluons do I have in a proton or in a quark? Let's say. For all that I'm going to do, a proton is made of 3 quarks, 3 valence quarks. So you just use the formula which I gave you before, namely this one here. The dx over x is taken care of by the fact that I multiply the distribution by x, and you integrate over k cap squared. And that integration produces a log, that is this log here. And this log is cut off at a scale which is of the order of lambda QCD. The reason being that when you think about protons as constituent of the proton, it doesn't make much sense to consider constituents which have a wavelength which is bigger than the size of the proton, which is essentially one of the lambda QCD. So there has to be a cutoff there beyond which the proton description stops to make sense. And this is what is lambda QCD represents. And now, so this is integrated gluon distribution for a quark. And that formula is also important for the following discussion. And I'm going to rewrite it in the following way. That's lambda squared over, up to Q squared, d2 k perp over k perp squared times phi of x and k perp. Where phi, you see, it's not integrated, it's the integrand. Phi is a non-integrated gluon distribution. And we will be playing with the two distribution. You see, phi keeps the information of the transverse momentum. X, g of x, does not. It is integrated up to the maximum value q squared. And both concepts are useful for a quark. It's enough to read the formula, just get rid of the log. This phi is just alpha strong CF over pi squared, over pi. CF is, as I said before, nc squared minus 1 over 2 times s. So now, what is going to happen is the following. This is a result of leading order perturbation theory. This is proportional to alpha strong, which is g squared. So you have the factor g from, you see, when you calculate the probability, you have to square, this is the amplitude. The vertex here is proportional to g. So when you square the amplitude, you get a factor g squared, and that's alpha. That's the alpha which is here. And then you have a log. Now, we are getting to a regime where it's not uncommon in physics, but it's often overlooked. It's a regime where alpha can be very small, let's say 0.1, 0.2, 0.3. It's not very small, but small enough. But the log can be big. So we are actually making an expansion in terms of alpha strong times the log. But what is the log? The log is reflecting the phase space for gluon emission. So it's a measure. Remember I told you this is the number of gluon between x plus dx. This number here is a measure of that number of gluons. So there are regimes, and this is important in QCD, where the coupling constant can be small, so the probability to emit a gluon is reasonably small. You can use perturbation theory. But the phase space available for this emission, which will eventually lead to the density of emitted gluon, is large. And under this condition, namely more precisely when alpha strong times log of q squared becomes over 1, naive perturbation theory breaks down. But you see, it breaks down not because the coupling becomes big, but because there are many, many particles around. And that is a situation which we know how to handle using various types of resonations, which I will explain now. Now, you may look in perturbation theory, when you have this situation, you may look at what are the dominant Feynman diagrams, the Feynman diagram which will be amplified by log. So there are diagrams which will contain the log and diagrams which will not contain the log. The diagrams which don't contain the log are not interesting because they are going to be small, because the coupling is small. But those which contain the log, we have to keep. And it turns out, it's a remarkable result that the dominant diagrams in perturbation theory are simple, I say what I mean by simple, cascade. And by cascade I mean the following. I mean, let's consider a balanced work. Let's consider a balanced work here. it emits a gluon, and the gluon itself can emit another gluon, etc. Maybe I will withdraw this on the chart. But this is what I mean by cascade. And of course, I'm not going to go through the proof, but you can start playing with Feynman diagram and see that indeed those diagrams contain logs, and other diagrams which you may draw, for example, I'm not going to draw because I may be making a mistake, but you can verify that other diagrams. This has been, I'm summarizing years of painful works here, but the situation is like this. So let me say more about this cascade, because it's an important issue. So, let me draw a cascade here. So let me assume, well, let me not specify what. So there is a momentum, an initial momentum, P, and then these gluons have a longitudinal momentum and a transverse momentum, which I call K1Z, K1 perp, and the last one is Kn, Z, Kn. Now, when I say it's simple cascades, it means that they are ordering of momenta. And there are two important orderings. One is ordering in transverse momenta. And that corresponds to what's known in the literature as the Dirac evolution equation. Dirac stands for Nochitzer, Grigor, Flibatov, Tareli, and Parisi, the name of the authors. And that ordering corresponds to K1 perp, smaller than K2 perp, smaller Kn perp. And what this says, so you see, when you sum up, when you consider that cascade, if you ask, let me put it differently. If you ask yourself, what is the probability to find in the proton a gluon which has a large transverse momentum, let's say Kn perp, then it is much more likely to find a large transverse momentum at the end of a cascade, like this, rather than through a single gluon emission. Each of these new branch of the cascade will be proportional to alpha strong at each vertex here, but there will be a log coming from each of these transverse momenta. And what I say in word here can be written in more complicated equation, which I will write in a second. But basically, the right question to ask is what happens if I want to find a proton with a large gluon with a large transverse momentum in the proton. It's very unlikely that it corresponds to a single emission from a valence quark. It will rather come from at the end of a long cascade of radiation. So that's a Dirac picture. And there is another ordering, which is not in transverse, but in longitudinal momentum. And the ordering in longitudinal momentum goes in the opposite direction. The longitudinal momentum K1 is bigger than K2, is bigger than K, and then. So the question you ask here is the opposite. I mean, it's not the opposite, it's the same type of question, but you ask, what is the probability to find a gluon with a very small longitudinal momentum? And this is what we are interested in, eventually. What is the probability to find a small X gluon in the proton? You see, what this cascade tells you is that this probability is higher at the end point of a cascade of successive gluon emission than it is at the beginning of the cascade, after a single emission. One characteristic feature of this cascade, if you think of it in terms of lifetimes of emission, remember the formula I had written before for the emission of a single gluon, the delta I, the lifetime of the fluctuation, was given by the following formula, 2kz, so this is now kz, kiz, divided by k curve squared, ki curve squared. So you see that the delta I, the lifetime of fluctuation, decreases along the cascade. So, if you think about this argument I was giving earlier about the lifetime and time dilation effect, you see that if you ask for gluons which carry a very soft momentum, longitudinal momentum, very small x, they will come from fluctuation at the end of a cascade, but this fluctuation have, in principle, a small lifetime because kiz will be small. However, if at fixed x you increase the momentum of the projectile or the target, that lifetime will be dilated and you will start seeing those partons which are at the end of the cascade evolution. Okay? So now let me give you a very simple, simplified version of the equation which govern this cascade, because I am slow.
You have, well, quite a
5 minutes, yes. Okay. Okay. Go much faster.
Does this scaling also have a name here? So we have DCLAP, but does this also?
Oh, yeah, I'm sorry. Yes, it has a name, of course. This is called BFKL for BFKL. This is Balitsky, Fadin, Kurev, and Ibadov. Yes, it has a name. It has a name, yes. So let me give you the equation, the DCLAP equation. So the equation which we want to write is we want to study how this integrated gluon distribution evolves when I change Q squared. So typically it's an equation which looks like this: d by dq squared of x, g of x and q squared. And that is given by the following equation: alpha star cf over pi. And let me replace cf by ca, and let me make a little note here: gluons only. So I'm ignoring quarks. Quarks can be treated, of course, but it's just unnecessary complication at this stage. Z, G, Q squared. So this equation is almost obvious. I mean, it's not obvious to establish, because we have to go through all the arguments that I was mentioning before and isolating the proper Feynman diagrams, but it has a probabilistic interpretation. You see, what is going on here is that you're asking what is the change in the gluon density for the momentum fraction x. So you want to consider all the process which takes you to x, and obviously all the process are coming from partons which have momentum z, which is bigger than x, and of course smaller than 1, because 1 is the total momentum of the incoming particle. So that's the boundary of the integral here. And then automatically this is 1 minus z, but we don't care about that because you look at the inclusive distribution. We're just interested in how many quarks or how many gluons I have at x. And that's given by the probability to split, which is basically this factor here, times the dz over z, which is a phase space for longitudinal, this is a longitudinal phase space, okay? Times the probability to have a gluon at z. So it's almost an obvious equation. Okay? Once you accept the fact that it is a probabilistic equation, this is almost obvious. Now, why is this equation important? Well, it is important because this Barton distribution has universal probability. That is to say, there is a meaning to the question how many gluons do we have in the proton? Because if you know how to answer this question in, let's say, in the context of one particular experiment, like the deep inelastic scattering, then you know that if you want to apply the same concept to another experiment, the same distribution function will be used. So there is a universal character of the distribution function. It's also important to realize that the absolute numbers is not accessible. It's only the change with q squared which is meaningful, which we can calculate from the perturbation theory. So only is calculable. So typically we have to solve this equation starting from some input at some fiducial q square 0, say, a couple of gv squared, and then evolve. But the value of the distribution at that particular scale at which you start, I mean, what you use as initial condition for this equation, is not calculable implicitly. So it's very important to keep that in mind. There are many things we don't know, but what we know and what we can calculate is the evolution. And finally, there is another property, and I will stop here. Yes?
This is a little typo. Gluon distribution in a quark should be in a nucleon?
This is a gluon distribution in a nucleon.
In a quark.
No. I calculated for a quark. This CF here means a quark. So I have a quark. I do perturbation theory. So nucleon is too complicated to calculate in perturbation theory. So I can't. I mean, I'm going to use a picture.
What do you mean when gluon distribution in quarks?
A quark is, as I said, well, it's probably right. The distribution. You see, it's a simple question asked for an electron. What is an electron? An electron is surrounded by a cloud of virtual photons.
In that sense.
In that sense. So you may ask, how many photons do I have in an electron? Okay. Okay. So now
Related to quark. Yeah.
it's related to quark because this is it's what I know how to calculate. Now the picture which I'm going to use for a nucleon and a nucleus will be a collection of independent valence quarks.
So that may be the
For the lecture.
third quark, because the quark should be elementary, yeah? So there's nothing in the quark, so it's third quark, so to say. Gluon distribution not in the quark. Third quark.
What do you mean per quark? Let's assume if I do perturbation theory in QCD, first thing I forget is about confinement and all these things. Okay? I have quarks and gluons, and they interact. A quark can emit a gluon. So first order perturbation theory tells me that there is an amplitude for a quark to decay into a quark plus a gluon. Okay? Now, I agree. That's mainly semantics. What I mean is that there is a matrix element which relates the bare quark state to a state with a bare quark plus a bare gluon. Okay? So now if I have a quark, dressed quark, or physical quark, so to speak, and if perturbation theory was very accurate, as it is in QED, you could ask the question, what is the probability to find a gluon in this particular dressed quark.
In the dress part. Okay.
Yes.
In that sense.
Yes.
The physical dress
In the
part is a
physical
kind of a
part.
complex object.
Yes.
Okay, yes. And this is for a quark. For the nucleon, my model of the nucleon will be 3 times this. It's not very sophisticated, but it's important to realize that it is not. There is no sophisticated confinement physics hidden here. It's just perturbation theory. Okay. The last thing I want to say before I close, and for the first lecture, is, and perhaps I will just say the word and come back to it after the break. There are important theorems and when I mean theorem, things we can prove, and this goes under the name of factorization. And it's so important that I will probably leave it here and come back to it after the few